Hari. Now in this part we discuss about launching of the satellite. So all the countries are sending satellite into the space, and therefore the space is all occupied by many satellites, artificial satellites. So if we want to send a satellite or launch a satellite, we have to decide first of all what's the purpose of the satellite. Accordingly, we have to decide an orbit first of all, and that orbit and the purpose and all that is put in front of an international agency for verification. Is because if that path is already occupied by some other satellite, we cannot use that. Or if that path we decided is crossing with any other path of the satellite, path of any other satellite, then that cannot be approved. So this international agency, if they give the approval, you can start constructing the satellite and also the rocket required for launching it. The purpose of the rocket is that to take that satellite to a particular height. This is now familiar to all because ISRO is sending rockets for other countries also. Many times you might have seen from the videos, and also the launch videos will be there, you can see downloaded. And this length of the rocket is of different depending upon the height up to which you are supposed to take the satellite. So actually from the ground we are deciding the height up to which it has to be taken. That's the only thing that we can do. But how we can define the height from the ground? That is a simple mathematical calculation. That suppose we want a satellite with definite time period t going around the Earth, and height to the satellite is h for that. Then there will be a definite orbital velocity for that. So connecting all this, we will be deriving an equation for h. Let us see. VO is equal to root of GME by small r, where r is the orbital radius desired. Then if t is the time period of revolution of the satellite around it, then capital T will be equal to 2 pi r by VO, where 2 pi r is the distance traveled in one revolution. So distance traveled in one revolution by revolution speed gives you the time period. Now from this, when I substitute VO equal to this much, therefore T will be equal to 2 pi r by root of GME by small r, you get. Now squaring on both sides, to remove the square root I get t square equal to 4 pi square r square divided by GME by r. Now from that equation I can have t square equal to 4 pi square r cube divided by GME. Yes. So we have got the condition between time period of revolution and the orbital radius. square directly proportional to r cube. Very important result. T square directly proportional to r cube. This is something called Kepler's third law. Okay, let be there. Now, what is our purpose is to find the height h for a time period t. So, from this I can rewrite this as r cube is equal to GME by 4 pi square into t square. Then r equal to GME by 4 pi square into t square all raised to 1 by 3 I cube root of the right hand side. Now r is equal to re plus h. So we have to bring height into that. Then re plus h is equal to GME by 4 pi square into t square all raised to 1 by 3 you are getting. Steps are very clear. Now, therefore, I can write the final formula for height h will be equal to GME by 4 pi square into t square all raised to 1 by 3 minus re. Now this is the simple formula for calculating the height for a definite time period t of revolution of the satellite. Now using this particular equation, we decide the height to the satellite or height up to which the satellite can be launched. Okay. Now, suppose I take in this equation t equal to 24 hours. Means time period of revolution of the satellite, I take it as 24 hours, that is the duration of a day. Then, with many other criteria, I can say that satellite is a geostationary satellite. Means, if I look at the satellite, I can see the satellite always at that point itself. Means, with respect to me, that satellite appears to be static. Such a satellite is called geostationary satellite. And I told you, this is not the only criteria for the satellite to become geostationary, but you can calculate the height to the geostationary satellite from the ground using this particular value put in this equation. Now, if I put that t equal to 24 hours into that one, I can see the value of h t equal to 24 hours. If I put in this one, then h will be equal to 35,800 kilometers, approximately 36,000 kilometers from the